Okay, so now we've learned our basic rules, our exponential rules and our log rules and our power rules and our sum and difference rule. We've learned our kind of basic building blocks for derivatives. Now we're going to learn two techniques that are going to open up our ability to kind of do derivatives of almost anything. So the first one we're going to learn here is called the chain rule. And what I want you to understand about the chain rule, the kind of the thought process around the chain rule, is think about what links on a chain look like, right? This is my wonderful artistic abilities. This is why I am a math teacher. Okay, so if you think about a chain, there are many links. And so when we're doing this rule, what it's saying is you can do this rule over and over and over and over as many times as need be to get through the problem. So what I'm going to do is start us off with a very small version of it, just to help us see what we're referring to when we talk about links in the chain. So what we're going to do is rewrite the function as a decomposition into two separate functions. So what we're saying is take your functions and look for, is there a function inside another function? So if you remember composition functions, that was like, or the fog problems. What we're going to do is instead of looking for the composition, we're going to decompose them. We're going to take them apart. So what I want you to do is take a peek, look at this function, and see if you can see one function inside another function. Okay? The inside function we're going to call h. The outside function we're going to call g. All right, so take a second, see if you can find it. I'll pause the video and take a guess at it. Okay, so unpausing the video. Here's how I see it. I see stuff on the inside. So we kind of think of that as like our inside function. And we said our inside function is called h of x. So our inside function might be that, 3x minus 4. And then we're taking that entire function and doing something with it. We're squaring it. So that outside function might be just h squared. Now, where did the h come from? Well, what we're doing is saying if our inside function is called h, how we have to think of this is it takes in x's and gives out h's, which means the g takes in h's and gives out g's. Okay, we're never going to do it again after this problem, but like this. So it's just to try to help you kind of see inside outside. All right, so now let's take derivatives of everything. What would be g prime of h? Well, that's a power function. So the 2 would come out to the front, and we'd be left with 2 times h to the first. Okay, what would be h prime? Well, h prime, well, we have x to the first, so that's 3 times x to the 0, which just makes x 3 times 1. Then the derivative of 4 is 0, so that just leaves us with a 3. So now what the chain rule tells us is the derivative of this function is the derivative of g prime of h times the derivative of h prime of x. So essentially what we're going to do is just take our outside stuff, which was 2h, and multiply it by 3. And when we do 2h times 3, that gives us 6h. All right, but we have to remember, what was h? What was h? Well, that was just here. H was the stuff that was on the inside right there. So what we're going to do is just everywhere we have a 6h, we're just going to replace that with every h with x, 3x minus 4. So, all right, ready? That kind of stinks, but the idea here, what I just want you to see one time, is it's the derivative of the outside function, and we leave the junk alone. Notice the h that was on the inside, we didn't do anything with it. It just stayed there. We just did the derivative of that exponent, brought it out to the front, made it into a 1. The inside stuff, that inside h, stayed the same. Then we did the derivative of the inside. We did the derivative of h, and that we got that value. Then we took these two things and multiplied them together. We multiplied them together right there, right? Okay. So now we're going to do the problem not using the rewriting it as the g of h and h of x. If that was kind of confusing to you, it's confusing to me. I buy it. I just like to look at it this way. This is how I look at it. My rule states, there you go. Do the derivative of the outside, leave the inside alone. Then multiply that by the derivative of the inside. So looking at this function, f prime. Okay, here we go. The outside function was that squared, right? So what I'm going to do is, what's the derivative of something squared? It's 2. Leave the junk alone. No matter what's inside of here, as long as that is a variable, leave it alone. Then the derivative of an exponent, you subtract 1 from it, making it a 1. Now, I call it the scratch out technique. I go up to the original problem where we started, and I say to myself, what have I done the derivative of? I did the derivative of the 2, so I scratch it out. Now, what have I not done the derivative of? There is still something on the page, so I times the derivative of that, the derivative of the junk. So what's the derivative of 3x? 3. What's the derivative of negative 4? 0, because that's a constant. So now I just kind of combine like terms and do all that kind of jazz, and I've got 2 times 3, which makes 6 times 3x minus 4. So you see, we get the same answer, just I don't know, it's a little mental math, a little bit of scratching out, but you get there. Okay, let's try 1,000 more. No, maybe not 1,000 more. Let's try a few more of these, though. Okay, so take a second, look at this problem, and see if you can identify inside, outside. If you think you see it, pause the video, try it yourself, and here we go. Okay, so how I see it, the outside is the squared again. I've got a whole bunch of stuff squared. How do I deal with an exponent? Well, I bring the 2 out to the front, leave the junk alone, subtract 1 from the exponent, so that makes a 1. And then I scratch out what I did the derivative of. I did the derivative of the squared. So now I got to go to the junk. What have I not done the derivative of? Well, the stuff on the inside. So what's the derivative of 3x squared? 6x. What's the derivative of negative x? Negative 1. What's the derivative of negative 4? 0, because it's a constant, so I don't need that. All right, now, so therefore, I can now kind of combine my terms, simplify stuff, and I'm not going to go ahead and distribute that through, actually. I'm just going to leave it just like that. For this class and for WebAssign, it will absolutely, not WebAssign, for MathAS, it will absolutely accept this as your answer. This is okay. Unless we were going to try and simplify, or we had a fraction we were trying to reduce or whatever, we don't need to worry about it. Leave it like that. It's good enough. Okay? So let's try this one. Here's one that's a little different. So again, we have to look for inside, outside functions. What's in, what's out. So if you think you see it, take a pause the video. All right, here we go. The inside function, we have to remember now, here we have an exponential function. And remind yourself, how do you know something's an exponential function? Well, it has a number in the base, and the variable is in the exponent, right? So therefore, it is exponential. So we need to use the exponential derivative rule. If you don't remember what that was, it is the natural log of the base times the exponential function itself. So when it was, it's the same function, it's the same, excuse me, I keep wanting to write e's. Go away, e's. Okay, so there we go. When the base is e, you just have to remember the natural log of e is 1. So therefore we end up with just our derivative being e to the x. Well, now in this case, we don't have just an e to the x, but we can still use our same logic here of, all right, inside, outside functions. We have e to the junk. So what we're going to do is do the derivative of e to the. How do you do derivatives of e to the? Well, it's natural log of the base times the whatever the function was itself. Notice we don't touch the exponential, the exponent part, because the rule says whatever your exponential function was, you just write it again. So here we did the natural log of the base, and then whatever our exponential function was, we write it again. So now we have done the derivative of the e part. So we scratch out the e. Now I say, what have I not done the derivative of? Well, I haven't done the derivative of x squared plus 7, right? So we have to do times, what's the derivative of x squared plus 7? Well, that would make 2x plus 0. So there we go. There's the 2x plus 7 part. And we have now completed our derivative because we scratched out everything. And if you wanted to simplify a little bit, you would say natural log of e is 1. So therefore, we would say the derivative of this function would be, and you could write the 2x in the front. That would technically be standard, more standard, but it doesn't matter. MathAS will accept it either way. So what we have here is 2x times e raised to the x squared plus 7. All right, let's try another one. All right, inside, outside, look for it, look for it. Okay, take a pause if you think you see it. Okay, here we go. We have to remember, what is the derivative of natural logs? All right, well, so for natural logs, the derivative of a natural log was 1 over x. Well, so now we know a little better. Instead of calling it x, why don't we call it u or something? So it would be 1 over u. It's just saying it's 1 over whatever was inside the natural log. So therefore, the derivative here of this function would be 1 over 3x minus 9. Now, for the fun part, let's do a scratch out. What did we do the derivative of? Well, we just did the natural log part, but I haven't done the derivative of the stuff on the inside. I haven't done the derivative of 3x minus 9. So what's the derivative of 3x? 3. What's the derivative of minus 9? Well, that's 0. So therefore, it just ends up being 3. Now this you could simplify a little bit, and I still don't think Math.AS makes you, but you'll notice if you kind of multiply fractions, you get a 3 in the numerator. I can factor a 3 out of the denominator, leaving me with x minus 3. So therefore that divides with that, giving us a final answer of 1 over x minus 3 would be our derivative. Okay, last one, I think. Give it a shot, take a little pause, see how this comes out, and all right, here we go. Now, this one is to help you see the chain part of the chain rule. We might actually have more than 2 links in this chain. So let's start with the outside stuff. What is the function we see on the outside? Natural log, right? Because then it's parentheses, all that stuff is the input of the natural log. So the derivative of natural log is 1 over whatever's on the inside. So that's 3 raised to the x squared plus 3x minus 4. All right, whatever. All right, now, scratch out what you did the derivative of. That was natural log. Take a pause, look again. What do we have here? Well, I have a 3 raised to the variable, so that's an exponential function. How do I do the derivative of an exponential function? Well, those were easy ones. It's natural log of the base, and then rewrite your exponential function again. Whatever you had on the page, write it again. Done. Now I've done, oops, I want to do that in another color. Oh well. Let me change. I'm just going to change it to another color. It's going to magically change. Okay, now we have done just the derivative of the exponential part, but we still have never done the derivative of x squared plus 3x minus 4. So times. Now notice, here's where you really get to see the chain rule coming into play, because we now have 3 links to our chain. We've had a function inside a function inside a function. All right, whatever. So here we go. So the derivative of x squared is 2x. The derivative of 3x is 3. And the derivative of negative 4 is 0. And there we go. And if you wanted to, you could always kind of simplify this stuff. And you'll notice when you start to have exponentials and logs inside each other, sometimes some interesting stuff happens. Because here we're going to have 3x squared plus 3x minus 4. And then times 2x plus 3. And then this is over 3 to the x squared plus 3x minus 4. And if you notice, we have these things are all multiplying each other. So, and we have something in the numerator and the denominator that are identical. We have that and that. So we are left with the derivative is equal to the natural log of 3 times 2x plus 3. So there you go. There's your chain rule. If you want to, now is a good time to pause the video or mark down the time and go try some of these problems. But if you feel ready, we can go and learn the other rule, and then you'll pretty much be able to tackle every derivative that we can throw at you. So the next rule is called the product rule. Chain rule was for functions inside of functions. Well, if you stop and think, what does the word product mean? That means multiplication. So what we're going to use this rule for is any function that can be broken up into 2 separate functions. One function of x multiplying another function of x. So an example here, if you take a look at number 11, would be something like this. Can you find your 2 functions here? I think it's pretty straightforward, only because they've broken it up for you with parentheses here. So you see we have e to the x, and then we have times 5x squared plus 3x minus 4. So, all right. Let's think of this as kind of this one as g of x and this one as h of x. Can you let's write these down. So g of x is e to the x. H of x is 5x squared plus 3x minus 4. Can you find the derivative of each of these? What is g prime? What is the derivative of e to the x? Well, that was the natural log of the base times e to the x, because it's an exponential function. And remember, natural log of e is 1. So therefore, we end up with just e to the x. What is the derivative of 5x squared plus 3x minus 4? Well, that's 10x plus 3. Now, the beautiful part about this is the product rule says what we do is we're going to mix and match. What we're going to do is take the answer to this and multiply it by the start of this. And then we're going to add that with the starting one of that times the derivative of that. So you essentially what it writes out to be is g of x times h prime of x plus g prime of x times h of x. So the way you can think of it is you take the derivative of one, leave the other one alone, plus do the derivative of the other one, leave the first one alone, or however you want to look at it. So therefore, our answer here would be the derivative of f prime is, I'm going to start with g of x, so that would be e to the x times 10x plus 3. Okay, and you can see that came from here and here. And then we're going to add that to e to the x times 5x squared plus 3x minus 4. So you can see that came from right here, e to the x, 5x squared plus 3x minus 4. And I'll write it down just below so you can see it. This was g of x times h prime of x plus g prime of x times h of x. Okay, so now more formally, it's right there, and you'll notice, does it matter which one you do first? If you do g for the derivative of g, leave h alone, then leave g alone, do the derivative of h, or not really, because if you think about it, it's plus, it's adding. So what do we know? Well, the commutative property holds. So this statement would be equal to g of x times h prime of x plus g prime of x times h of x. And you could switch around the g's and the h's if you wanted to. You could rewrite this as, you could write the h prime first and the g next, because it's multiplication. And what do we know about multiplication? It's commutative too. So you don't have to stress too much about order, which one you do first, which one do you do second. Don't let that get into your mind. All you got to remember is you do the derivative of one of the functions, one of the factors, leave the other one alone, and then add to the derivative of the other one, the one you haven't done, and leave the one that you did the first time alone. All right, so let's practice this. If you think you got it, give number 12a a shot. Pause the video. If not, you can watch along. All right, so let's break this up. I see this as natural log of x times x squared plus 5x minus 1. So what would that be? All right, I'm going to do it this way, and this is how I like to do it when I'm kind of in the wild doing this. Math just for the fun of it. I always just do the derivative of the first thing. What is the derivative of a natural log? 1 over x. Okay, so I did the derivative of something, so then I leave the next thing alone. Did the derivative of one factor, leave the next factor alone. Plus, all right, now I got a flip-flop. I already did the derivative of natural log, so I have to not do the derivative this time, but I'm going to do the derivative of the next part. Voila. Okay. That's number 12. I hope that worked out for you. Let's take a look at 12b. 12b. Okay, so now this one's a little bit bigger. And somebody might say to you, well, do we even have to use this? Couldn't we just distribute this through? Absolutely. You could just distribute it through. You enjoy doing that while we use the chain rule or use the product rule and not waste a half hour multiplying all this stuff through. All right, so pause the video. Pause the video if you want to try it on your own. All right, here we go. The derivative of our first factor, and you can look at it here. We have this whole function multiplying this whole function, right? Okay, so the derivative of the first factor would be what? Derivative of x to the fourth would be 4x cubed plus 6x minus 2, and the derivative of 5 of 0. Okay, so then since we did the derivative of the stuff in yellow, we have to leave blue alone. So that's going to be x to the 17th minus x squared plus 5x minus 1. All right, now plus, now we flip-flop. Since I did the derivative of the yellow the first time, I have to leave it alone this time and do the derivative of the blue, which would just be simple. 17x to the 16th, power rule, minus 2x plus 5, and there you go. And once again, we do not need to worry about simplifying this at all. You type this into Math.AS just like this, you're fine. You do this on your midterm, you're fine. So don't worry about simplifying it, just worry about kind of getting your order. Okay, so there we go. Now on to number 13. Now, just because we learn these rules separately doesn't mean they can't be used together. You'll notice in this problem, we have a product rule because we have one function here multiplying another function here. And then you'll also notice the yellow function is a chain rule because it's a function inside a function. So someone once asked me this great question, which was, which one do you do first? And I say you always do product rule first. You always look for how can I break these up into smaller derivatives. Then once I have it broken up, if I have to use chain rule, I'll use it then. So that's kind of the easiest way. Now I'm sure we can run into an instance where you'd actually start with the chain rule. But well, actually, I guarantee you I could write one where you start with the chain rule. But it's kind of if you can do a product rule first, I feel like it makes the problems easier. But sometimes you can't. Sometimes you have to do it the other way. So here we go. The derivative. All right, well, since we found a product rule, we have something times something. Let's start with the yellow. How do I do the derivative of x squared plus 5x minus 1 all raised to the third? All right, chain rule, because we have something on the outside. So do the derivative of the cubed first. Bring the 3 out to the front. And then we leave the junk alone. Everything that's in the inside just stays how it was. All right, now that we've done the derivative of the cubed, we can kind of scratch it out and say, okay, now we got to do the derivative of the stuff on the inside. So that would make what? 2x plus 5. Now, that was just doing the derivative of the yellow part. This right here is just the derivative of the yellow. I have not done the blue part. I still have to leave the other factor alone. Okay, now I've done my first derivative. Now I've done the first part of my product rule. So I now say plus. Okay, now leave your original function alone. Leave the yellow part alone. Here, and I'll kind of color coordinate that. There's the blue. Okay, so now we left the yellow alone. So now what we're going to do is do the derivative of the blue. Oh, and we've got another chain rule. Okay, what do I do if I have something to the 19th? Well, all right, we drop the 19 down, and we leave the junk alone. Whatever's on the inside, don't touch it. All right, there we go. Now we did the derivative of the outside. We scratch out that. Okay, what have we not done the derivative of? X cubed. So that would make it 3x squared plus 4. Fantastic. So now we have done the derivative of the blue stuff. Fantastic. So we have now done the whole problem. Wonderful. All right. So that's going to bring us to problem number 14. One more where it's kind of just another practice problem. So give it a pause, give it a try, see how you do. Okay, so what did you recognize on this one? Is this a product rule or a chain rule? It's chain rule. All right, good. Sometimes when we start mixing these up, students like to make natural log. They try to think of this as times, but no. It's a function. This is the input of natural log. So therefore, it's chain rule. So therefore, it's just 1 over all the junk. Then don't forget to do the derivative of the inside, which is, since we did the derivative of natural log, now we're going to do the derivative of the stuff we haven't done. So that would make it 3x squared minus 5. Fantastic. Alrighty. And there's your answer. And if you want to, you could always write this up here in the numerator. It's fine. Whatever you want. Okay. Then I want to throw one more problem at you. This one will just be a little bit of extra that we didn't have on the sheet. How about this? Let's try this. Y equals the natural log of x cubed minus 5x plus 2 times 4x cubed. Okay, so now this problem, take a look, see what you see, take a pause. All right, you're ready to go. This problem, you see, has natural log, and we are multiplying that function times another function there. So therefore, we're going to break this up using product rule, but we also have a little bit of chain rule. Lots of fun. So derivative of natural log, that is 1 over your junk, x cubed minus 5x plus 2, times the derivative of the inside, which would be 3x squared minus 5. And then now, this stuff here was just the derivative of the yellow, right? Because the 1 over stuff was the natural log part. Then we had the derivative of the inside, which was that part. Now we have to leave the blue part alone, which is 4x cubed. Okay, so now that we got that, let's go ahead and add that. Now we got to switch them. Leave the yellow part alone, what we originally had, which was natural log of x cubed minus 5x plus 2. Okay, that was the yellow. Just the original yellow, no derivative done. Then times, now we got to do the derivative of the blue. What's the derivative of 4x cubed? Is that exponential? Is that power? How do you tell? Well, remember, exponential has the variable in the exponent and the number in the base. This has the number in the exponent and the variable in the base. So it's just a power rule. It's the simple, basic, good old, bring the 3 out to the front, which would make 3 times 4 is 12, x squared. Voila! There you go. All right, so that's about it for these rules. But I do want to throw one more rule at you. It's another rule. We had power rule, we had product rule, and this one kind of pairs up with product rule. But sorry, not power rule. We had chain rule and product rule. This one pairs up with the product rule. It's called the quotient rule. So remember, product means multiplication. Quotient means division. So what this rule is going to say is we might have a function where it looks like we have one function over another function. So for example, it might look something like this. Y equals, let's see, x squared plus 3x minus 4 divided by e to the x, let's say. So do you see we have one function over another function? Now, there's lots of ways we could attack this, but let me kind of show you an idea here. You will never have to repeat what I'm about to do. Just going to show you where the quotient rule comes from. So what I've done, if you remember, negative exponents, this does not mean inverse. This is a negative exponent. Let me rewrite it this way to make it a little more clear. There we go. So what I've done is brought my g of x up to the numerator by giving it a negative exponent. So now do you see we have one function multiplying another function? We already know how to do that. That's a product rule. So let's do this very theoretically. We're not going to actually know any numbers or anything. We'll just say, all right, the derivative of f of x would be f prime of x. Leave the other function alone. Plus, now leave the f of x alone. But here's the fun part. We've got a chain rule here because we have the negative 1, right? So we have to bring the negative 1 out to the front. And then from that exponent, we have to subtract 1, which would make it negative 2. Okay. Then we have to do times the derivative of the inside, which would be g prime of x. Okay, so take a pause, make sure you followed all that. I'm not going to do anything on this step other than a little bit of algebra simplification. Any negative exponents, I'm going to drop them down to the numerator. So here you see I have the g of x to the negative 1. So that's going to leave me with f prime of x over g of x. Now, here this negative 1 and a positive, I'm just going to turn that into a minus. F of x times g prime of x divided by g of x squared. Okay, so now the rules for adding and subtracting fractions says we have to have common denominators. So to give myself a common denominator here, what I'm going to do, I'm going to go ahead, just give myself a little more space. I'm going to go ahead and multiply this denominator here by g of x, but whatever I do to the denominator, to keep it balanced, I have to do it to the numerator. So therefore, that would leave me with y prime is equal to f prime of x times g of x, and then over g of x squared minus f of x times g prime of x over g of x squared. So look at that, we've got our common denominators. So I'm going to go ahead and combine these now. So that gives me f prime of x times g of x minus f of x times g prime of x, whoops, go away, all over g of x squared. All right, so there's our quotient rule. So what we can do to kind of make our life a little bit easier is memorize, 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 so we don't have to come up with this every single time. So let's look at where these things started from. What started in the numerator? What started in the denominator? Well, f started in the numerator, g started in the denominator. So notice what we did. What in this first term here, we said, all right, the thing that was in the bottom, the thing that was low, times the derivative of the high, minus the high times the derivative of the low, all over the square of what's below. Do you hear the little rhyme? Okay, so what we're going to do, how I write this, is low d high minus high d low over the square of what's below. Hopefully that you can get that little rhyme. It'll help you remember this, and it makes these problems a little more simple, a little easier. So we've gone through all that, so I'm going to clean this off because I'm sure you can rewind the video and see it there. And let's do this problem using our little rhyme. Okay, so here we go. Let's do our problem. The quotient rule, once again, you should have it on your notes, which was low d high minus high d low all over the square of what's below. So here we go. Low times the derivative of the high, low d high. So what's the derivative of x squared plus 3x minus 4? Well, that's just, what did I say? Excuse me, 2x plus 3 minus the derivative. So we did low d high minus high. That did not want to go. Let's try that again. There we go. High d low. What's the derivative of e to the x? That's the easy one. It's itself, e to the x. All over the square of what's below. There we go. There's our derivative. So hopefully that helps. Quotient rule. It's worth the few minutes it takes to memorize it, just to speed you up and get you through some what would be really, really hard problems. It makes them a little faster and easier. Okay. So I believe we have now finished every single derivative rule that you're going to learn in this class. Fantastic news. So you're ready to start working on all of your homework problems, except for anything that mentions the word marginal. The next video is going to talk about marginal, and it's not a new derivative technique. It's just a way of it's another way of hearing what a problem's asking for. It's a word problem verbiage. So go practice every single derivative problem. Make sure you can do them all, and feel free to ask questions if you need any help. Best of luck.